Good morning, everyone. So last time we have seen DES algorithm, the count, all the steps that were involved in that are involved in DES. Now let us look at the decryption. It is very simple. If you have understood the DES algorithm, uh, then if you just have to implement the keys in the reverse order for decryption. Otherwise, the complete process is same. So let me just show you. Right. So if you just, this is the process that we have seen for the encryption, IP, round one, round two, and so on. Okay. Uh, so this is a complete encryption. For the decryption part, you just have to provide for the first round, you just have to provide K16. For the second round, K15, and so on. So obviously the decryption will be uh, performed. Second thing, that whatever the ciphertext you are getting during the encryption, that will change. So that will be the input for the decryption, and whatever you will get as a output after the decryption, that will be the plain text. So there will be two changes. The input will change, and the keys in a sequence, the sequence of keys will change. Okay, so that's a simple step that is needed for the decryption. And if you think of, brute force attacks, so what are the possible number of keys that you can have? That is 2 raised to 56 bit. So because the key which is used for the DES is 56-bit key. So if you want to know how which key is used, so the number of keys are these many keys. Okay, and when you start thinking of trying all those keys, you'll need at least 1,000 years to break the DES. Okay, but so DES was secure for almost around 17 to 20 years, just because of the S boxes. Okay, now there are multiple variations of DES. You can have double DES or triple DES, where what you have to do is, remember, for the 16 rounds of encryption, you are using 156-bit key. Okay, so just think of this key. Okay, one key you are inputting for the algorithm, and then you are generating these 64-bit keys. Okay, sorry, 16 keys. These are the sub keys, but the key which you are using is only one, right? So in triple DES, what happens is you get the plain text as an input to the 16 rounds of encryption, and then you are using one key. Okay, whatever the output is generated, okay, that will be given for the decryption part using some other key. Okay, so you are implementing decryption for the ciphertext, but you are not using the same key, you are using the different. Okay, and whatever the output you are getting, again you are doing the or following or executing the encryption, okay, with the third key. Okay, now why you are doing this? This is just to add the complexity of the for the algorithm. Okay, it will definitely increase the security of DES. Okay, and then you are actually generating the ciphertext. Okay. Now for the decryption in triple DES, what we have to do is the ciphertext will be uh, gone into a decryption first. Okay, so whatever the keys you are generating, you apply those keys in a reverse order. Okay, then you apply for the encryption, and then you apply for the decryption. These keys also are used in reverse order. So K1, K2, and K3 will be used in these steps, okay, where encryption, decryption, encryption will be performed, okay, in 3 steps. While decryption of triple DES, what you have to do is you have to process these 3 steps in a reverse order. So decryption, encryption, and decryption. Okay. And the second change is these keys you are using, they will be used in a reverse order, K3, K2, and K1. Okay. So that way you can produce the plain text. Okay. So this is a very simple technique. If you have any doubts, please ask before we go ahead. In double DES, you process encryption and decryption with 2 keys, and for the decryption of double DES, decryption and encryption. That's it. But in triple DES, encryption, decryption, encryption, and while decryption, decryption, encryption, and encryption. Now there are some weaknesses of DES, okay, because it was not very secure. The only thing is hackers were there, but they could not break that DES for many years. But finally, they could break DES in 1989 or 90s somewhere. The problem was in the S box. I told you the complete security lies in the S box. How those S boxes are generated is not known to everyone. So the first problem is in SBox 4 there are few bits which were designed. The hackers could find out what was the relation between those two numbers, but the S4 box was weak by that logic. Okay, once that S4 block was broken, it was very easy for the hacker to break all the remaining S boxes. Okay. The other weakness was if you are providing some input to S box, this and you are getting the output. If you are repeating that, for the multiple times, you are getting the same output. Okay. So there's no change in the encryption. So that is another weakness of this DES. So these were the reasons why DES was broken, and the hackers could find out the relation of all the S boxes, how those S boxes were designed. Okay, another weakness was D box. D box means what? If you have noticed here, you are applying some initial permutation, then you are applying at the end you are applying some inverse initial permutation. So you're telling the world that the first bit is going at the 48th location and so on. What is the use of these things? If everyone knows that this bit is going there, then there is no actually there's no security. Why you are using that step? There's no point in using that step. So that is the distribution of text. Excuse me, I have a very important call. I have to get this. Yes, Colonel Abhishek sir. Extremely sorry, guys. Right. So this was the problem of DES. Then we needed a new cipher instead of DES because DES was broken in 1998 or around. But for the hacker, it took 22 hours for breaking the DES when it started. When a hacker does that, he has to report, the NIST that he's breaking the DES and it is not secure anymore. This is actually the ethical hacking, and this was the organization who broke that DES. Now, the problem was 56-bit key. It's a very small key for encryption at that uh, era. So uh, that that is the one that has to be solved. So NIST again did the same thing. He got the tender, and the new encryption standard was developed. That is advanced encryption standard. Okay, now this algorithm is so secure, not just because of the key size. Now, if you have noticed, AES uses these many keys. These are the size of the key: 128, 192 bits, and 256 bits. You can use any of these three size keys. And instead of 64-bit block, it processes or encrypts 128-bit. Okay, so these are two changes for the input that AES has done. And believe me, no one has uh, broken AES yet. AES is secure still, uh, still at this moment. So, and the reason behind it is the big key size and obviously the algorithm himself. So we'll see the algorithm, actual algorithm, right? So there are key sizes are different. Okay, 128-bit key, 192-bit key, and 256-bit key. At all the key sizes, the block size is same. 128-bit block you are encrypting at a time. Okay. There are different number of rounds when you are using different number of keys, size keys. Okay. So in DES, there were only 16 rounds all the time. It is fixed, right? So in this, that is the change, another change in AES. 10 rounds for 128-bit key, 12 rounds for 192-bit key, and 14 rounds for 256. Okay. And then you have different things. Let us not discuss these things right now because you'll not understand those things. Let us try to see what is the algorithm. Okay, how does the algorithm works? Now, if you have noticed at AES, sometimes you're working with 64, sometimes you're working with 56, sometimes you're working with 48, sometimes you're working on 32-bit. So the number of bits you're working on at any operation level are different. Okay, so that complexity is removed in AES at all the times. At any given step in AES, you're working with 128-bit data. Okay, so for understanding purpose of AES, it is very simple. You're working with 128-bit data at a time. Okay, now with this 128-bit data, you are going to prepare a matrix. Okay, so 1 byte is a 1 cell. Okay, like this, there are 16 bytes. Obviously, 16 bytes will form 128-bit. Okay, and I hope you know all these terms: 1 byte, 1 word, and all these things. Right. So whatever the input you are getting, 128-bit, you are going to prepare a matrix. Okay, 4 by 4 matrix, and you are putting all the bytes in there, right? And obviously, some operations will happen on the inputs, and then you'll get the encrypted text, okay, ciphertext. Just you have to remember that at every step you have to work with the matrix itself. Okay, so now we'll see the details. Now, when you're talking about the key generation part, obviously, just like this, there will be the encryption part, there will be some rounds. Okay, this is a DS I'm talking about, but even AES performs the similar structure because it also works on the feastal function. Now, there are some 10 rounds, 12 rounds, or 14 rounds instead of 16 rounds. And there is a key generation part also, which has to be there. Okay, for 10 rounds, you'll need 10 keys. For 12 rounds, you'll need 12 keys. So there is a sub-key generation algorithm that you'll need. Okay. Now, as I have told you that every given step, there has to be a 128-bit data all the time. Okay. So be it input, be it a key or sub-key. Okay, key is also, let's say, consider 128-bit key. The sub-key which you are generating, that also has to be a 128-bit key. Okay, so these are all 4 words of the input. And for sub-key generation, if you are generating 128-bit sub-key one sub-key, so how many such sub-keys you will need? 10 sub-keys for one. So you need all those 44 words, such 44 words for all the keys. So how many data you are generating, keys, number of words you are generating for all the rounds, that is given below. Okay, I'll tell you how these sub-keys are used, okay, in a while. But this is just a bird eye view of AES. Okay, please do ask me the question any moment, any slide. Let us discuss all the queries instead of just explaining these algorithms. Okay, now this is an overall picture of AES algorithm, right? So as you can see, every step will have that 4x4 matrix. Okay, that is 128-bit data. Either you can say 16 bytes, you can say 4 words or something like that. Okay, anything is okay. So these are some of the steps, these are some of the rounds. Then round 1 will have some 4 different steps. Even in the DS, there was a few steps of each round. Okay, similarly, in AES also, each round has some steps. Okay, I'll tell you what are those steps. Step by step, we'll try to see what exactly what happens at each step. Okay, so plain text is a 128-bit. Then you are preparing a matrix that will be called as input state, okay, S0, S1, and so on. Then you will have to apply some initial transformation. Okay, that initial transformation will change some of the data. Okay, then you are putting that in the rounds. Okay, there are 10 rounds. Why we are talking about n-1? N depends on the size of the key. If the size of the key is 16 bytes, then your number of rounds are 10. If it is 192 or 192 bits, then 12 rounds, and 256 bits key, 14 rounds. So n depends on the size of the key. So let us consider the 128-bit key, the first one. Okay. So if the 128-bit key is provided to the algorithm, okay, this sub-key generation algorithm will create 10 such sub-keys. Okay, and for each round you'll need a one sub. And then after all the rounds, you will produce a ciphertext. Okay, so whatever the matrix you are getting here, it will be a ciphertext. Okay, so this is just a bird eye view. We'll now see actual steps. I have explained all these things. This is just for your reading. Okay, right. Now there are 4 stages in each round. Okay, we'll see those 4 stages one by one. One is called as substitute byte. So S box is there. Okay, just like DS, AES also has the S box. Okay, then you have shifting of rows. So some data has to be shifted. Okay, then mixing of columns. Now, if you remember, there is a D box in DES. The bits positions are changed. Here, instead of changing the bits position, we are using a mix column here. I'll tell you what, how does it work. Okay, but just right now we are just trying to see what are the names of these steps. And then at the last there is a simple XOR operation. Okay, so when we go further into the algorithm, okay, what you have to do is these steps. How does these steps looks like? The plain text. When you get the plain text, what you have to do is you have to add that to a subkey 1. Okay, so that means this is a XOR operation. Okay, a simple XOR operation. So that is the first step in the AES. Then whatever the output of that is there, that will go into the input as an input to the round 1. Okay, and so on. So there are 10 rounds as a first case. Substitute bytes, S boxes, shifting of rows, changing of the bits, mixing of columns. There will be a multiplication that we have to perform in this step. And then again, this step is repeated, adding of or XORing the data with the next subkey. Okay. Now, if you remember, there are 44 such words that are to be generated by the what you can say this key generation wizard. Okay. Now, as you are generating 44 words here, the subkeys from the first subkey, 128-bit key, will have first 4 words. So if you go back, yeah, this one. So when you are generating the subkey generation algorithm will generate all the keys here. How these keys are stored? They are stored in an array. 44 such words are stored. First, when the first 4 words are provided to the round 1, it will form a 128-bit key. I hope I'm connected. Am I audible? There's a power cutoff just now happened.
No, sir, you're audible.
Okay, thank you.
Yes, sir, you're audible.
Thank you. Oh, sorry. So first 4 words will form 128 bits, and that will be provided to the first round, and so on. Okay, so that is given over here. So W, that is the complete matrix. Okay, and first 4 words, 0 to 3 words, are provided to the round first round. Okay, and so on. Now, if you look at the decryption, okay, what exactly changes in the DES? What has happened? The round steps are not changed, but the keys are provided in a reverse order. In AES, the same key is used in the rounds. The only thing is the rounds are reversed. Okay, So instead of reversing the keys, we are reversing the rounds itself. Okay, so instead of like see mix column, shift rows, and substitute. So those 4 steps will be reversed in in that round. Okay, so instead of changing the sub keys. One more thing to notice here is the last round steps. Okay, if you have remembered, if you have noticed, there are 4 steps in each round. Okay, round 1, round 2, and so on. But in the last round, there are only 3 steps.